Good afternoon. Thank you for joining us today for No More Downtime. This is Dennis Nash. I'm the president of Control Station and the principal cheerleader of both our award-winning optimization technologies and our expert team of process control professionals. I'm joined today by Dr. Bob Rice, Control Station's Vice President of Engineering, and today's presenter. Bob leads the company's R&D efforts. He also oversees our field services group. He's a recognized expert in multivariable process control and model predictive control. He's widely published. He's been the featured presenter at a number of industry conferences. So today's session is based on No More Downtime, a publication originally released by Control Station last year. We'll begin with a brief overview of downtime's impact on both production and profitability. Bob will then delve into 5 key performance indices that can be used to uncover performance issues that consistently lead to mechanical failure. Bob will conclude with a pair of case studies where the same KPIs were used, and once they were applied correctly, they helped improve plant performance. Within today's time constraints, those of you who have joined us will be able to share your questions directly with Bob and with me. So the U.S. Department of Energy published data and analysis linked to the performance of domestic manufacturers. Their data focused on the cost-benefit of technologies used to actively monitor the health of production equipment. And in terms of benefits, their analysis documented significant reductions to both the time and the cost associated with unplanned downtime. From other sources, the global cost of downtime has been estimated at nearly $650 billion annually. And that estimate makes the projected ROI seem right on target, that ROI from DOE. So let's now take a look at select industries and get a more granular view of how downtime affects them financially. In the No More Downtime publication, we also referenced some findings from GE, General Electric. Due to their market reach, GE continues to be a great source of data. And in their analysis of the oil and gas market in particular, GE examined the effects of downtime across the supply chain. Downtime's effects run the gamut from extraction and refining to distribution and consumption. Financially, downtime cuts into a manufacturer's top-line revenue by reducing production levels. The figures shown here are large, which is generally expected from this sector of the process industries, but equally large is the impact of downtime on bottom-line operating profit. If we transition to the basic materials sector, we see that unplanned downtime, again, primarily impacts production as well as equipment maintenance. The latter may not come as a surprise. This is a physically abusive sector. Accelerated wear and tear on production equipment plays a key role in their downtime calculus. Our publication noted that downtime affects the average plant with losses of 5% in production and between 30 to 40% in profit. Big values. Looking at specific financial costs here in mining, we get a clearer sense where those values come from. A number of individuals who have registered for today's session are from the broader basic materials sector. I imagine the data resonates with them. Lastly, we look at the power and utilities segment. Like the previous two, downtime is credited with increasing maintenance costs and lowering output. The economic analysis here points again to lost revenue and reduced profits. This is an unfortunate formula that repeats itself across all quarters of the process industries. So let's start with the bullseye. Often at the heart of mechanical failures and its associated downtime is mean time to failure. Some refer to that as mean time before failure, mean time between failure. Each is a reliability measure. MTTF can be linked to an OEM's value rating for full strokes if a valve, a damper, or other process-related equipment. But in general, variability in the process data tied to chattering, cycling, and chasing behavior unnecessarily accelerates mean time to failure. The No More Downtime publication highlighted a select group of KPIs. The 5 metrics shown actively measure a process's dynamics in terms of that relate directly to mechanical health. Dr. Rice will now offer a more thorough review of the 5 metrics before he shares a pair of related case studies. Bob will show how improved loop performance and reduced downtime are 2 sides of the very same coin. So with that, Dr. Rice, the stage is yours.
Thank you very much for that introduction, Dennis. What I'd like to do is take you through a few of the metrics and what they mean and how they can be related to downtime or mechanical issues at your facility. An important metric that helps understand the pattern or the variability in your control loops is the likelihood that the loop is oscillating. Loops that aren't oscillating, that are nice and flat and stable, are the ideal case, right? Everything's tracking set point, your output's not moving around, your process variable's not moving around, you're able to maintain set point very effectively. That's ideal. When your process starts to stray from that ideal behavior, starts chasing itself, starts oscillating due to mechanical, due to upstream variability, due to interactions, due to poor instrumentation, these things can increase the wear and tear. If you have a control loop that is oscillating, that means that that control valve, that damper, that valve is working a lot harder than what it needs to be able to maintain control. So being able to filter out the loops that are oscillating, to be able to get a list of these are the top 10 loops that are highly oscillatory, these are the ones that give you opportunity for improvement. Oscillations can really impact the lifespan of final control elements like valves and dampers and pumps. In this case, this metric, likelihood of oscillation, takes a look at the frequency within the process variable and helps you get an understanding of, is there a dominant oscillation in it, and what is the likelihood that this loop is oscillating. Obviously, if you look at the process variable trend, you can see that clearly the loop is oscillating. And so if you're looking at it, you say, yeah, of course it's oscillating. But if you have several hundred or several thousand loops, going through each trend independently to identify an oscillation is far too time-consuming. So having a metric that can calculate this and then filter it up to you in a report or in a UI, that's going to help you identify these loops much more quickly. Metrics related to the wear and tear of your final control element are metrics such as output reversals and output travel. And these do exactly what they sound like they do. The output reversals is the number of times your output changes direction. How many times does it chatter around trying to maintain it? Is it constantly back and forth around a small area to be able to maintain control? Versus output travel, which is how many full strokes per hour is the output moving to maintain control. This output travel can be directly related to mean time between failure for most of your mechanical elements. A lot of valves, actuators, positioners actually have a lifespan of total number of travels, full strokes that they have between maintenance, between failure. So trying to track output travel is very important for being able to track mean time between failure. If you know how often or how much movement your control valve is making in full strokes per hour, you can estimate how long it will take to reach the end of life. Additionally, output travel can be related to plant air or how much resource is using to drive that valve. So if you can decrease the amount of output travel, you're going to decrease the amount of resource needed to actually drive that actuator, which is a small amount of savings, but still an important one. The longer you can get your valves, your dampers to live, the longer you can extend their life, the less time you're going to have to put towards downtime. When your output travel increases or your output reversals increase, that means that you're starting to increase the amount of wear and tear in your elements. An increase in wear and tear is obviously something you want to track down and be able to identify. So being able to sort and prioritize loops that have high output travels and high reversals is a good way to be able to find the low-hanging fruit of opportunity for valves and dampers that are being overworked. Output distribution is basically a way of looking at where your output is spending a majority of its time. Is it starting to operate against constraints? Are you always hitting the upper control limit or the upper physical limit of your valves? Are your valves always hitting at 100% or at 0%? If they're persistently slamming against their constraints, you're not going to be able to have good control. You could also start physically damaging your equipment if you're constantly slamming against those constraints, open the seats, with the seals and the actuators and so forth associated with those mechanical elements, right? You want a final control limit to operate in the middle of its range, generally in the green area. You don't want it operating at 5%. You don't want it operating at 95%. You want it where it's designed to operate. Not only is it going to perform better, but these types of instrumentation, like valves, like dampers, like pumps, are more linear in the middle of their operating range, and so you'll get much more consistent control, much better behavior, okay? Also, if you can operate closer to those constraints or closer to the better operating, you're going to extend the life of your equipment, okay? Additionally, if you have valves that have leaks in them, like you're getting flow past the valve even though the output is showing 0% or 5% or some very low value, these output distribution plots can actually help you identify places where you're starting to get leak past your particular system. Everyone's favorite topic when you're talking about dampers or valves is stiction, right? Stiction is basically the valve not behaving as it should. It's sticky friction. You're telling the valve to move, but the valve doesn't actually move, right? A lot of times you tell the valve to move 0.1%, it's not going to move. You tell it to move 0.5%, it's probably not going to move. You may tell it to move 2%, and it may not move. All of a sudden you tell it to move 3%, that valve unsticks itself, jerks open, and now that process variable is going to go much further than what it needed to, okay? Now that you've gone too far in one direction, now the valve's got to work its way back, and so the output's slowly going to, ramp down to try to bring the process variable back. The process variable is not going to move until you've suddenly moved 2 or 3%, which is too far, and it's going to pop the other direction. And so you get this oscillation that tends to be either in a sawtoothed or square wave type of response. So having a metric that can go out and actually identify loops that exhibit this behavior without having to go through multiple process variable, controller output trends, be able to interpret the charts and graphs yourself, having metrics to be able to identify this, to be able to prioritize which valves have high likelihood of stiction, which ones have a high amount of stiction, can help you design your downtime much more effectively. So if you've got a planned downtime, you can go ahead and replace or service particular valves that are having issues. So if you can correct them before they fail while your process is running, that's obviously a much better outcome. So I want to go into a couple of examples where these metrics helped identify some of the bottlenecks at the facility and helps prevent some of the unplanned downtime. So a really good example came from the SAGD oil extraction, which is essentially a oil retrieval process where you pump steam into down into the ground, into these the bitumen reservoirs. The steam integrates with the oil, and it helps loosen it up, and then they can pump that kind of liquefied bitumen back up out of the wells, right? But that requires a significant amount of steam and a significant amount of resources to push all that steam down into the ground to be able to retrieve this bitumen, okay? So one of the important aspects of SAGD oil production is the ability to provide consistent and cost-effective steam into the wells. And so when you're running a steam gen plant, one of the most important things is to be able to understand the steam quality. The higher steam quality that you have, up to a certain point, you have this kind of constraint that you want to operate. Too high steam quality can actually start to pit some of your equipment. You want to operate as close to that upper constraint as possible. And so what we wanted to do was start to understand, what are the variables that are contributing to the variability in steam quality. So one of the first things that we did was we noticed that there was a steam quality oscillation. And so we could actually identify this oscillation and identify loops that share this frequency of oscillation. And I'll show some examples of how we do that in a few slides. But these Diction-induced oscillations on these high-pressure boiler feed water loops are actually increasing the variability of the steam quality. And so this Diction, even though it's not very much, which you'll see in a moment, are the primary factors that are causing steam quality variability. So when you're looking at these particular steam quality loops, you can start to see that you've got these frequencies of oscillation, which are about 3.6 minutes or so. We can see which other loops actually share those frequencies. Okay, so you have all these high-pressure boiler water controllers that have the oscillation, but it's interesting, they're not the same. You have some other loops that are actually playing in that steam quality at Plant 2. Okay, and so when you're looking at Plant 2, you're starting to see this oscillation present in these other loops, and we can actually perform correlation analysis. So you can actually see which loops are contributing to the interaction within those systems. So we can start to see that our steam quality is lagging behind the impact of the O2 trim controller. Okay? So we can actually start to narrow down and say, well, our primary variable of focus is steam quality. The variable that's influencing that the steam quality is following behind is that O2 trim controller. Okay? We can take a look at that O2 trim controller, and we can actually trace down that particular controller has Diction associated with it as well. And so you have all these mechanical elements that are driving variability into your loops. And to be able to have tools that trace out, these are the loops that are driving these oscillations from the hundreds of other loops that are in the steam plant, whether they're, the inlet or the outlet or the fuels and so forth, you can actually go and figure out which loops are contributing to those oscillations and what are the issues with those loops. Are there tuning issues? Or in this case, there are mechanical issues, right? And so we're able to trace down, which particular valves are influencing our primary variable of interest, okay? In this particular case, this 1 kPa swing in the fuel gas pressure and 100 kilogram per hour swing in our airflow is directly attributing to a 1% swing in our steam quality. So by correcting those issues, we're able to actually improve our steam quality tracking by almost 1%. Another example would be from the basic materials. This is a ceramic propant plant. Ceramic propant are basically small beads that they used to pump into the ground when we were doing a lot of fracking. They would pump these beads in, and as the ground was fracturing, these beads would actually hold open the fractures in the ground to allow natural gas to escape much more consistently. And so to create this propant, these small beads, you would actually spray dry a clay slurry. You'd run it through a dryer, you'd run it through a classifier and a ball mill, and basically push it out. So it's a very, it's a very simple process. It's a basic materials process. There's only a couple hundred loops that are in this entire process, but each one of those loops are important. One of the important areas and the cost of the propant is actually a lot of the materials that they add at the beginning, such as ammonia, into the slurry to be able to improve the flowability of the material through the pipes. And so when you're adding ammonia, obviously ammonia costs money. Clay is much cheaper than ammonia, and so they were really worried about how much ammonia they're actually applying into the process. And so they have a number of control loops that are used to ratio out the ammonia based off the clay feed and based off the formula that they happen to be running. And so what we wanted to do was understand what was going on in the ammonia control loop. And what was interesting is there were a couple of things going on, but one of the metrics that we looked at was what is the output distribution, what's the output average. And what they found is that as they were tracking, they actually started to see valves start to fail. And what happened in this particular application is under normal conditions, under normal flows for this ammonia, which are around 16 and a half for a flow, 1 month their output average was 11%, but they were getting the same flow rate when their output was at 5%. They didn't change the pump speed, they didn't change the supply. What was happening is that valve started to get a lot more flow by. It's starting to, the seat of the valve was starting to wear out. And even though they were closed, they were actually getting flow past it. That was actually less than the flow meter could actually read. And so they actually were able to use this tool to say, look, you know what, we're starting to operate at a much lower value than what we had been in the past. Let's take a look at this valve and figure out what's going on. They went out there and they saw that ammonia was actually slipping by the valve even though it was closed. And so by looking at the average output or looking at the distribution of the output when you're starting to get saturated, you know, those constrained outputs limit the controllability of the loop. And in this particular case, they were actually showing that there was flow by going by on these particular control loops. So, you know, these examples just kind of show some of the different ways these metrics can use to help understand the mechanical aspects of your plant. Your mean time between failure, how often do you have these mechanical elements fail at your plant? How many times do you have control valves fail, or how often do they start to behave so poorly control becomes near impossible, right? Do you start to have lots of oscillations or variability with those control valves because you've got stiction, because you've got deadband and other poor acting dynamic behavior? So being able to, you know, understand what is driving your final control elements, be able to identify metrics to help you identify which valves are starting to fail, help you understand the interaction between your loops, help fight some of those physical constraints so you're not constantly operating at 100% or 0%, can help you eliminate downtime because you can identify these issues early and correct them during a planned downtime. You can take this corrective action, you can perform root cause analysis by understanding some of these relationships between your loops.
That was a great presentation, Bob. Thanks for sharing the background on the metrics as well as the 2 case studies. We'd like to open it up to today's participants for questions. Please use the chat function within WebEx to submit a question. While we're waiting, a question that typically comes up, Bob, is that related to stiction. And in particular, what metrics are available that customers can use to understand stiction in a meaningful way?
So stiction identification is all about pattern recognition. Stiction is a very repetitive pattern in the oscillation. It's not a simple sine wave. It kind of has those sharp corners. And so metrics that are focused on stiction tend to be very focused on pattern recognition and what those stiction profiles look like. It's also important to understand how much stiction does your control valve have. You know, if you've got an oscillation that's being caused by 0.2% stiction, well, that may be the limit of the control valve. You may never be able to achieve better than 0.2% stiction. Versus if you've got a control valve that's experiencing 4 or 5% stiction, that's obviously something that can be corrected. And so when you're looking at metrics, you want to look at, yes, do I have stiction or not, but also how much stiction do I have in the valve, because that's going to tell you whether or not you can actually take corrective action on that particular control loop or not.
You know, another question that we often get relates to specific processes, and one that we often encounter is the dryer. You know, what specific attributes of the dryer and the KPIs might you offer up to provide some insights to our audience?
So when you're dealing with things like dryers, you really want to understand the amount of energy going into those. Drying is a very energy-intensive process, and so you really want to focus on metrics that help you understand how much energy is going into that dryer. And those relate directly to output travel, output distribution, your average controller output value, how close you're tracking temperature. You know, these metrics can be used to help understand how much energy is going into that dryer. If you're able to maintain tighter tolerances around your set point, you may be able to lower your set point to a lower value that's still achieving the constraint or objective that you have. And so if you can lower the set point because you've got better control and now your output is now running at 28% versus 30%, you may have just saved yourself 1 or 2% energy while still maintaining the same amount of control. And so the metrics that you're looking at, you really want to focus on the energy consumption of the particular application, especially when you're talking about drying and furnaces and ovens and things that require a lot of energy to operate. You also want to make sure that you don't have final control elements that have a lot of stiction or a lot of oscillation, because if you're having to move that gas around a lot, that instability is going to cause you to use more gas than what's necessary.
Great answers. So with that, we've not any additional questions from the audience. We'll conclude today's webinar. Thanks very much to all of you who have joined us today. Thanks to Dr. Rice for his remarks. We hope that you'll join us again in the future for another WebEx on topics related to process control and plant-wide optimization. On behalf of all of us here at Control Station, thanks. Have a great day.